Okay, 3.2 notes, we're going to talk about graphing logarithmic functions. So in 3.1, we graphed exponential functions, so when our x was in our exponent. Today we're going to be graphing log functions, which is actually the inverse of exponential. So exponential and logs are inverses. When we talked about inverse functions this year, how we solved for inverses was we flipped the x and y. So same thing works when dealing with exponential and log graphs. If I make my x's the y's and I make the y's x's, so just flip the x and y, that's how we come up with one graph versus the other. So if I had this point, which was 0, 1, I have the same point on my other graph, but instead it's the inverse of it, so it'd be 1, 0. So they are symmetrical about y is equal to x. So they're symmetrical on this diagonal line. They will always be symmetrical on that line. So our log graphs start down low and then go to the right, just like how our exponential graphs start close to 0 and then go up to infinity. So they mirror each other on that x is equal to y line. So the graph that we were looking at on the last page works for positive bases. So in log graphs, our base is what's going to tell us. So when our base is greater than 1, we have a graph that looks like this and is in that shape. When our base, so that little number down below on the log, when it's a fraction, so if it was some type of fraction in between 0 and 1, then our graph goes in the opposite direction. So it would start close to 0 and then get further away. Some basic characteristics of our log function. So if I just had log base whatever number, if I had log base 4 of x, these would be my basic characteristics. So the x-intercept is 1, and there is no y-intercept. So notice here that we don't cross in either one of these. We don't cross the y-axis. So there is no y-intercept, and our x-intercept is 1. The y-axis, or x is equal to 0, is our vertical asymptote. So this is our vertical asymptote where x is 0. If b is greater than 1, then the function's increasing, just like this one, it's increasing. When b is a fraction, it's decreasing, so this one is decreasing. And the graph is smooth and continuous. It has no sharp corners or gaps. So it's a function. All of our functions are smooth, continuous, and have no sharp corners. So to find the domain of a log function reverses the domain and range of the exponential function. So before, for our exponential function, our domain was always negative infinity to infinity. Now for our log function, our range is negative infinity to infinity. And where our range was positive numbers, so it was from 0 to infinity, now our domain is going to be from 0 to infinity. And it shifts with horizontal shifts. So before exponential, shift with vertical shifts. Log functions shift with horizontal shifts. So our domain could change, this number could change if we shifted to the left or to the right. So to find the vertical asymptote, this is super important here. To find the vertical asymptote, we set whatever is in the parentheses equal to 0. So our log function may look like y is equal to log base 7 of x plus 4. So to find our vertical asymptote, we take what's inside the parentheses and set it equal to 0. So x plus 4 is equal to 0. I would subtract 4 on both sides, so x is equal to negative 4. That is my vertical asymptote here. And when our vertical asymptote changes, so usually our vertical asymptote is through 0, but when that shifts to negative 4, that means our domain also shifts. So that would mean for this example, our domain would be from negative 4 to infinity. So whatever our vertical asymptote is, that's what number repeats in the domain. Our range for this example, for all log functions, our range is negative infinity to infinity. And then to find the x-intercept, we plug in 0 for y. So just to continue with this example, because questions will look like this on like WebAssign and the quiz that we have next week. So we would plug in 0 for y. So I have 0 is equal to log base 7 of x plus 4. To solve a log function, so to solve a log function, the only time we'll have to do this is to find the x-intercept. But to solve, we start with the base. What it's equal to becomes our exponent, and then what we're taking the log of, so what's in the parentheses over here, goes on the other side of the equal sign, so x plus 4. So we just flip the order that it is. So in here, it looks like it's 7 raised to the power of x plus 4. It's not, it's log base 7, but those two will never be on the same side. So if they're on the same side here, they're not on the same side when we flip it. So this, again, is how we find our x-intercept. From here, we would solve. So 7 to the power of 0 we know is 1, because anything to the power of 0 is 1. So I have x plus 4 is equal to 1. I would subtract 4 on both sides. So x is equal to negative 3. That is my x-intercept, but when I write my x-intercept, I have to write it as a coordinate point. So I plugged in 0 for y and got x is negative 3. So negative 3 comma 0. So again, this example is super helpful. It looks like the ones on the WebAssign and it looks like the ones from the quiz. So questions, when it asks you to graph and find everything, will look like this. It'll need the vertical asymptote, domain, range, x-intercept. On the next couple pages, we're going to talk about graphing them, but this is how to find all of our important information. So this slide, super, super, super important. This slide talks about the transformations. So same type of transformations apply to our log functions as our exponential. When you're adding outside or subtracting outside, that's a vertical shift. So when you're adding, we go up. When you're subtracting, we would go down. When you're adding or subtracting directly to the x, adding means that we're going to go to the left. Subtracting means that we go to the right. So that's when you're directly applying to the x, it's a horizontal translation. We have a reflection on the x-axis when it's outside. We have a reflection on the y-axis when it's inside. So a way to remember that is you want to keep your x's outside of your house. Like if you had an ex-boyfriend, you keep them outside. So it's a reflection on the x-axis when it's outside of the parentheses. And then when you multiply by a number, if it's a number that's greater than 1 on the outside, that would be a vertical stretch or shrink. And then if you have a number being multiplied on the inside, if it's greater than 1, it would be a shrink. So it's the opposite when it's inside. If it's greater than 1, it's a shrink. If it is less than 1 but greater than 0, so a fraction, it would be a horizontal stretch. All right, so to graph. We're going to start by graphing our exponential function. So to graph exponentials, we talked about this in the last video for part 1 of 3.1. We start by plugging in numbers. So I plug in values for x, plug them into my function there, and get some points for y, some points on our graph. So good numbers to plug in are -1, 0, and 1, but we talked about in class today that you could plug in whatever numbers you want. You could keep plugging in as many numbers as you want until you get some points on your graph if you happen to have points that were too big. So 3 to the power of -1 makes it the reciprocal, so that would be 1/3. So I plugged in -1 and got 1/3, so I'm going to put that on my graph. Go to the left to -1, up 1/3. Then plug in 0. I have 3 to the power of 0, which is just 1. So I plugged in 0 and got 1. And I can plug in 1, so 3 to the power of 1 would be 3. So 1, 3. Go to the right one, up 3. Then I can connect my points. With our log graph, our x's can become y's and our y's become x. So we flip our points. So my first point on my log graph is going to be 1/3, -1. My next point is going to be 1, 0. And then my last point will be 3, 1. So I'm going to go to the right 1/3, down to -1. I go to the right 1 and stay on 0. And then go to the right 3 and go up 1. And there's my graph. Be careful because you don't want to cross your vertical asymptote here. So for this graph, our vertical asymptote for the blue one would be x is equal to 0. Because usually we would set whatever's in the parentheses equal to 0, but here we don't have anything, so it's just x is equal to 0. So our graph is not going to cross the vertical asymptote. So it'll get really, really close, but doesn't cross. And then to find the other parts, we can find the domain, which would be 0 to infinity. Because looking at our x values, we get really, really close to 0, but don't touch, and then our graph goes to the right forever in infinity. Our range would be -infinity to infinity. For log functions, it's always -infinity to infinity. And then here our x-intercept, where we cross the x-axis, is at this point, which would be 1, 0. So x-intercept is where we cross the x-axis. So we could plug in 0 for y and solve for x. But here we could just visually see it on our graph. So I'll plug in 0 for y just so we can see. So using this function here, we're looking at our log one. If I plugged in 0 for y, so 0 is equal to log base 3 of x. I start with my base, and then the other two flip positions. So x is equal to 3 to the power of 0. So x would be equal to 1, which is the x in our x-intercept. In this graph, since we have that same log base 3 as we did in the last one, we can just take that last graph. So I had a point here, here, and here. So this was our log graph. And I can apply the transformations. So when I have a negative on the outside, that's a reflection on the x-axis. Remember, we keep our x's outside of the house, so when it's outside, it's on the x-axis. And then I also have a -1 on the x. So minus on the inside when it's happening directly to the x, that would be a shift to the right. So we move to the right one. So my graph goes to the right one. I take all of my points, just shift them to the right one. So this point should have been at 3, 1, so our line goes like that. Same thing. But I shift all of my points to the right, and now my new graph looks like this. But I also have to do that reflection on the x-axis, so my x-axis is here, so it flips on the x-axis. So if I'm 1 point away down here, I need to be 1 space away up top. That point stays the same, and if I'm 1 space away here, I need to be 1 space away down low. So my graph now looks like this. So we just flipped it on the x-axis. So we flip it about that line. So my graph is this pink one here. So the basic log base 3 graph, so this is log base 3 of x, would be the blue line, but my graph here, my g of x, is this pink line. I had to apply my transformation 1 to the right and then reflect it on the x-axis. Just for fun, we can find all of our basic characteristics. We need the domain, range, vertical asymptote, and x-intercept. So to find the domain, we want to find the vertical asymptote first. To find the vertical asymptote, we set whatever's inside the parentheses equal to 0. So x minus 1 is equal to 0. Add 1 to both sides, so x is equal to 1. So our vertical asymptote is x is equal to 1. It is a vertical line, so it has to be x equals, don't forget. And then the domain goes from 1 to infinity. It's still going from 1 to infinity because this arrow points in the right direction, so it's getting bigger x values, so it's going to infinity. Even though we flipped it on the x-axis, it's still going to the right, which are large x values. Larger x values. Our range is always negative infinity to infinity. And then our x-intercept, we have to plug in 0 for y. So I would have 0 is equal to negative log base 3 of x minus 1. The 3 is our base. We flip the other 2, so it's equal to x minus 1, and our exponent is 0. The negative doesn't matter because I could always divide both sides by -1, and 0 is still 0. 3 to the power of 0 would be 1. X minus 1 is equal to 1. I add 1 to both sides, so x is equal to 2. So my x-intercept would be 2, 0, which we have that point on our graph here, that pink dot. So, all right, for the next one, we're going to find the domain, x-intercept, and vertical asymptote for our log function. So to find the domain, range, vertical asymptote, and x-intercept, we want to start by finding the vertical asymptote. So we set what's inside the parentheses equal to 0. So x minus 5 is equal to 0. I'm going to add 5 to both sides. So x is equal to 5 is my vertical asymptote. And that means my domain goes from 5 to infinity. My range is always negative infinity to infinity with log function graphs. And then my x-intercept, I'm going to plug in 0 for y. So I have 0 is equal to log base 4 of x minus 5. Start with my base, which is 4. Flip the other 2. So 4 to the power of 0 is equal to x minus 5. 4 to the power of 0 is 1 because anything to the power of 0 is 1. X minus 5 is equal to 1, so I add 5 on both sides, so x is equal to 6. So my x-intercept is 6, 0. So I'm going to go ahead and plot that point. I go to the right 6, stay on 0. Now I'll also plot my vertical asymptote too since I have that. So my vertical asymptote goes through 5. And my graph is just shifted 5 to the right because it was a -5. So that means we go to the right 5. So when I plot my graph, it's our basic log function graph. So it starts down low, really, really close to our asymptote, and then just slowly gets bigger like that. So that would be my graph. Next, we have our natural logarithms. So log function with base e is called the natural log. If I had log base e of x, that is the same thing as saying ln of x. So log base e and ln are the same. Log base e is our natural log, so ln is natural log. The domain of our natural log is all the real numbers greater than 0. So it's the same properties as our log functions. We just can't plug in to x like -1. If you put ln of -1 in your calculator, you'd get an error. So can't be anything less than 0. Also, if you put a ln of 0 in your calculator, you'd also get an error. So find the domain, x-intercept, and vertical asymptote of the log function and sketch the graph. So here, we're doing the same. We can change ln to be log base e if we want. It has the same characteristics of the last 2 graphs that we did. Notice how one of them was log base 4, the other one was log base e. We still do the same, or the other one was log base 3, sorry, but we still did the same thing. So to find the domain, range, vertical asymptote, and x-intercept, let's do the same thing. We set what's inside the parentheses equal to 0, so x minus 3 is equal to 0. Add 3. X is equal to 3. That is my vertical asymptote. I can go ahead and graph my vertical asymptote too. So I put a vertical line through 3. My range is always from -infinity to infinity. My domain is the same value as my vertical asymptote, so it'll be from 3 to infinity, and it's always parentheses. And then to find my x-intercept, I want to plug in 0 for y. So I have 0 is equal to ln of x minus 3. ln is the same thing as saying log base e. So to put this in exponential form, I start with my base, which is e, switch the position of the other two, so e to the power of 0 is equal to x minus 3. E to the power of 0 is 1, because anything to the power of 0 is 1, so x minus 3 is equal to 1. Add 3 to both sides. X is equal to 4. So my x-intercept is 4, 0. So I'm going to go to my graph, put a point at 4, stay at 0. And then the only transformation I have here was I went to the right 3. So my graph has that basic log function graph like this. And we know that it goes increasing this way because yesterday we talked about it. E is like 2 point something. If you put it in the calculator, it'll evaluate it for you. It's 2 point whatever, but it's not a fraction, so that's why we know it is an increasing graph. Because remember, if our base was something that was less than 1 but greater than 0, then our graph would have this type of shape like that, just the opposite way. But here it's increasing because log is greater than 1.